So I am Debanjan. I am from IIST Sitpur, and I am with the Department of Electronics and Telecommunication Engineering. And my actually talk is related to the hierarchical MnO2 Nanoflowers based emission room temperature alcohol sensor. So these are my structure of the talk, and now first come to the motivation part. So from the problems with the commercially available gas sensors are like they are the high operating temperature, they poses the sluggish response time and recovery time, as well as the high fabrication cost. So the people are actually working on the development of room temperature paper sensor, which causes the fast recovery and response and recovery dynamics, as well as high sensitivity at room temperature. So this is actually the methodology of my work. First, I use some low-cost technique like hydrothermal route for synthesis of MnO2 nanostructures. Then I study the effect of reaction time on hierarchical nanostructures, and then I use as a biomarker. I use some alcohol compound as a target gas. Then I also propose the sensing mechanism. So now first question come to our mind that why I chose MnO2, because it exhibits high catalytic activity and towards oxidation of VOCs, but it is also widely used in chemistry but not widely explored for the gas sensing device application. And also it has half-filled d orbital electronic structures. That means it has multiple stable oxidation states. And also the interesting properties of this kind of MnO2 nanostructures are the it possesses multiple polymers, kind of alpha, beta, gamma, and delta. So due to that things, this property, so you can easily fabricate 1D, 2D, 3D hierarchical nanostructure using some low cost hydrothermal technique. So now, why the hierarchical nanostructures are also beneficial for the gas sensing? Because this kind of structure possesses large surface area. It enables fast gas diffusion in all direction, kind of 3D direction. It possesses, that's why, and also fast transport kinetics it offers. Now this is in the material synthesis part, where I use the the KMnO4 as a precursor solution for MnO2, and then and also added some reducing agent like HCl. And the main part of is that by keeping the temperature constant, I varies the reaction time by for 3 hours, 5 hours, 7 hours, and the different kind of nanostructure, hierarchical nanostructure was obtained. So first going to the sensing or the other characteristics, I want to explain about the growth mechanism of the hierarchical nanostructure. First, due to that kind of solution, first MnO2 nucleus formed, and then the nanosheets, the formation of nanosheets was observed, and then in processing steps, first due to the Oswald ripening process, the nanoflower like structure, then the mixing of nanoflower and nanorod, then finally nanorod like, and also you can see that archin like structure often. For the experimental evidence, we also we also got the FSM image for defined hours. Say for 1 hour, which is nanosheet kind of structure was obtained. Then for 3 hours, due to Oswald ripening, we obtained the nanoflower like structure. Then for 5 hours, the mixed structure of nanorod and nanoflower. Then 7 hours, the archin like nanorod mixed structure. And then at last, I will not show for the details about this structure. At 9 hours, I obtained some kind of etching due to that HCl and obtain the nanotube like MnO2 structure. So this is whole about the growth mechanism and the successive steps which I have obtained for different experiments. Now the morphological characterization for the duration, the reaction time with 3 hours, that is sample S3, I obtained the flower-like structure where the nanosheet is of thickness of 50 nanometer. From the same image also you can see the which is actually from the lattice spacing, which is correspond to the delta phase. Delta phase is nothing but the nanosheet of the nanosheet like structure. And for the sample 5, that is duration reaction time with 5 hours, the mixed structure, and which is from the lattice spacing of 10 image, it is also confirmed the nanosheet which is delta phase and nanorod which is of alpha phase. So both kind of phases are in with these structures. And for the duration time of sample, 7 hours, I obtained the nanorod like structure, and the lattice spacing is matched with the alpha phase of the MnO2. And also these kind of phases and all these things also investigated further using the X-ray diffraction, and there you can see that for the 3 hours reaction time, that is delta, and for the 7 hours, that is alpha. But in case of 5 hours, the both are there, that means alpha delta. So I also studied the surface composition analysis for these 3 samples for Mn2p, all these characteristics. But this from that slide, I can conclude that the average of oxidation states of these 3 samples are less than 4, which indicates the presence of mixed valence set for Mn, that is Mn3 plus and Mn3 plus and Mn4 plus. And then I also observed the K2p peaks, which suggests the presence of intercalated K plus ions. And in this, what is the importance of this intercalated K plus ion? That it stabilizes the crystal structure of MnO2, and in order to accommodate the K plus ion, few Mn4 plus ions eventually get reduced to Mn3 plus ion, which further strengthen the presence of mixed valence set like Mn4 plus and 3 plus. These are the main things which are actually used for the sensing to get the significant amount of enhanced sensing performance for MnO2 structures. So why I am discussing, I will talk more discuss later on these things, why this Mn3 plus and 4 plus are important. No, now from this slide, I just there is actually little bit time over this. That's why I just choose sample 3, and the electrical and the gas sensing study of the sample 3 is are actually going to discuss. So first, for the electrical characterization, I try to define what type of conductivity is positive. So from the electrochemical impedance spectroscopy, I found there is a positive slot which actually so I was electrical characterization part. So from the electrical characterization, I got the n-type slope, that positive slope that implies the n-type conductivity of the sample. Then also, as for the device, my device was very simple, that is the gold contact deposited on top of the MnO2 nanostructure. To I also investigate the current voltage characteristics of the device and found it's a ohmic contact between gold and MnO2. Then I also investigated the effect of temperature on the baseline resistance. I found that the baseline resistance decreases, which is typical of a nature of a semiconductor. And also another important thing is that from the Arrhenius plot, I got that the activation energy of the surface is lower than that of higher temperature. So the gas regarding the gas sensing study, the important thing is that and the interesting thing is that I observed the p-type response. That means however this is a n-type material, but although in presence of reducing gases like alcohol, I got the p-type response. That's very anomalous and astonishing. So to try to find out what is the reason behind it. So I also further investigate. This is by the device schematics. What is the nanoflowers, and on top of I also deposited the 2 gold electrodes. Here you can see that it's the room temperature response magnitude. After room temperature, it's decreasing with increasing temperature. Here you can see that methyl, in case of methyl, ethanol, and 2-propanol, these the alcohols, the resistance is increasing. Then it's saturated, and when gas is off, then it starts decreasing. So that thing, although it's a n-type material, but resistance is increasing in presence of reducing vapor. That means it is a kind of p-type response. So and also repeatability, we got this kind of characteristics in repeatable manner. Here is only 2 cycle have been shown. And also I also observed the response magnitude variation with in the range of 10 ppm to 800 ppm for 3 different alcohols, and plotted in a this response magnitude versus concentration plot. So now the important features of my sensors are, it is although n-type sensor, but also but it exhibits p-type response. The sensor exhibited room temperature sensing performance towards these alcohols, and the response magnitudes are also significantly high. For 800 ppm, you can see that this 88% response, with response time is also appreciable enough because it's a room temperature sensing, that is 47 seconds, and these are the data for my gases. So now what is the sensing mechanism for this kind of anomalous response? So that presence of air, this is actually the MnO2 structure. This is the layer. Okay. So layer by layer structure. Here you can see the Mn interstitial and the potassium intertided ions over there. And in the presence of molecular oxygen, actually get tapped by the oxygen vacancy on top of the MnO2, and they trap the free electrons. That is Mn3 plus actually then release electrons to the conduction band due to the charge balance, and that is Mn3 plus convert to the Mn4 plus. But on the other hand, in presence of methanol, what happened? The methanol reacts with these adsorbed oxygen ions, then they trapped electron releases. These trapped electron actually trapped again by the Mn interstitials, and free electron associated with the Mn interstitials decreases. That's why the device resistance increases in presence of methanol, like reducing gases. So for this hypothesis, I also tried to experimentally validate such hypothesis, and I also performed the XPS characteristics before and after adsorption. I found that there is significant amount of reduction of Mn4 plus, but the Mn3 plus and 2 plus are increasing. Here you can see after adsorption the and before adsorption data, where the Mn4 plus is decreasing, but Mn3 plus and 2 plus are increasing. So that's the reducing, due to that reducing effect, the resistance is increasing. Okay. This is a conclusion where you can see that this type of the sensor we obtained, and I would like to acknowledge CSIR, ISTC for my institute, and thank you for your kind attention.